Welcome to the deep dive. It is March 18th, 2026, and today we are looking at something that is probably sitting in an open tab on your browser right now.
Almost certainly.
Right. So picture this. You are trying to learn something complex, like maybe you're teaching yourself to code or, you're brushing up on some heavy statistics for a work project.
Yeah, we've all been there.
And you hit a wall, you just get completely stuck. So what do? You copy the problem, you paste it into a generative AI chatbot, and instantly it just spits out this perfect, elegant answer.
It's like magic.
Exactly. It feels incredibly helpful in the moment. You nod, you copy it back, you move on with your day. But the underlying question we really have to ask is, did you actually learn anything?
Well, I mean, the short answer is usually no. It's the ultimate illusion of competence.
Right.
We so easily confuse the AI's capability with our own
Hmm.
simply because, the interface makes it totally seamless to access that final answer. We feel smart because the machine is smart.
And that tension, right, between just getting an answer and actually building a lasting skill, that's the core of our source material today. We are unpacking this fascinating paper by Dr. Jonathan H. Westover. It's titled Adaptive AI Tutoring in Education.
It's a fantastic read.
Yeah.
Really eye-opening.
It really is. So our mission today is to look at why these early sort of reactive AI chatbots might actually be a massive trap for learners. But more importantly, we're going to explore how a completely new approach is changing things.
Right, by combining large language models with reinforcement learning.
Yes, which is creating this system of scalable, personalized, productive struggle. Okay, let's unpack this. What exactly is the trap of the answer machine?
So the trap is rooted in what educational psychologists call the novelty effect.
Okay.
Like when generative AI first arrived on the scene, I mean, the hype was just astronomical.
Oh, totally. It was everywhere.
Right. Everyone thought we had this conversational oracle that would democratize education overnight. But the data tells a very, very different story.
Really? How so?
Well, particularly when we look at traditional digital learning environments. The paper points out that in MOCs, massive open online courses.
Oh, yeah, those huge online university classes.
Exactly. The completion rates for those typically hover around an abysmal 5 to 15%.
Wait, 5 to 15? That's terrible.
It is. And that is despite incredible production value, expert instructors, a wealth of accessible information. The enthusiasm just crashes hard and fast.
Okay, but wait, I want to push back on that a little bit.
Sure.
Because if I'm stuck on a spreadsheet at work, like friction is the enemy, I don't want a full lesson. I just want the
Yeah.
formula so I can finish my report and meet my deadline. Why is getting the answer instantly considered a trap?
Well, because you were confusing executing a task with learning a skill.
Ah, okay.
If your only goal is finishing the spreadsheet today, then absolutely use the chatbot, get the formula.
Right.
But if your goal is to actually learn data analysis so you can build the next spreadsheet from scratch, then the chatbot is, well, it's like a GPS that just teleports you to your destination.
Teleports you.
Yeah, like, sure, you arrive at the restaurant, but you never learn the streets. If someone asks you the next day how to navigate that neighborhood, you're completely lost.
Wow. Yeah.
You didn't learn the city. You just learned how to push the teleport button.
Okay, I see the distinction. So the problem isn't the information itself, it's that teleporting completely bypasses the cognitive work.
It completely bypasses it.
Yeah.
And the paper highlights this crucial metacognitive gap.
Metacognitive gap, meaning what exactly?
Metacognition is essentially thinking about your own thinking.
Okay.
To use a reactive chatbot effectively as an actual tutor, a learner needs to know exactly what they don't understand. And they need to know how to ask the highly specific questions required to bridge that gap.
Which is hard.
It's incredibly hard. Most learners, especially beginners, they simply do not possess those self-regulation skills yet. They literally don't know what they don't know.
Which means they just default to asking for the answer. So if true learning requires navigating the streets, like you said, allowing you to hit traffic, make a wrong turn, and actually figure out how to correct yourself, how do we build a system that guides that journey?
Well, that's the big question.
Right, because it would need some kind of brain capable of tracking your exact location on that learning path.
And historically, the brains of educational technology have been incredibly rudimentary.
Like how rudimentary?
Well, the old adaptive systems used something called Bayesian knowledge tracing. which is basically just a mathematical way of tracking binary signals.
Binary meaning just what, yes or no?
Exactly. Did you get the answer right or did you get it wrong?
Hmm.
If you got it right, the system checks a box that says you've mastered the concept and it just moves you on.
Oh, wow. Which feels like judging a gym workout solely by whether or not you successfully lifted a heavy barbell once.
That's a perfect way to put it.
Like, it completely ignores your form. It ignores how much you're sweating. It ignores the fact that it might have taken you 5 minutes of intense, agonizing effort to get the weight up there, or, if you had to drop it twice before succeeding.
Right.
A binary right or wrong system just completely misses the actual process of getting stronger.
And that physical analogy translates perfectly to cognitive effort.
Hmm.
I mean, in complex domains like programming or advanced mathematics, you almost never get the code right on the first try.
Oh, never.
Right. A missed semicolon triggers a syntax error, which results in a wrong answer.
Hmm.
But that doesn't mean you fundamentally misunderstand the logic of a loop.
Yeah, it's just a typo.
Exactly. And this is where Dr. Westover's paper introduces the modern solution, which is reinforcement learning, or RL.
Okay.
Instead of a binary checklist, RL formulates learning as a sequential optimization problem. The University of Pennsylvania actually implemented this.
Okay, what did they do?
They use what is called a partially observed Markov decision process, or a POMDP.
Wait, hold on. A partially observed Markov decision process.
Yeah, no.
That is a massive wall of academic jargon.
It really is.
Let's break that down for everyone listening. Partially observed makes sense to me because the AI obviously can't physically see inside your head. It's just guessing your knowledge state based on clues.
Right.
But the paper also mentions they combined it with something called Bayesian particle filtering. What on earth is that?
Okay, so think of it like a tracking system trying to find a submarine in the ocean.
Okay, I'm with you.
The system can't see the submarine directly, right? So it scatters thousands of hypothetical dots or particles across a map, representing all the places the submarine might be.
Oh, okay.
And every time the system gets a sonar ping like a clue, it sweeps away the dots that don't make sense, which narrows down the true location.
That's brilliant.
Right. In this learning system, the particles are different hypotheses about your brain.
Wow.
Instead of just right or wrong, it maintains this continuous multidimensional estimate of your knowledge.
Multidimensional. What kind of dimensions are we actually talking about here?
So it tracks 3 specific parameters. First, your initial performance level. Second, your learning speed, meaning how fast you adapt when you're presented with new information.
Okay, that makes sense.
And third, your mastery ceiling, which is where you currently top out in complexity. So as you answer questions and interact, it sweeps away those incorrect models until it pinpoints your exact cognitive state.
So it essentially has this highly accurate evolving map of my brain.
Exactly.
How does it use that map to decide what question to throw at me next? Because that's the whole point, right?
And what's fascinating here is how it makes that decision using model predictive control.
Model predictive control.
Right. It's kind of like a master billiards player lining up a shot.
Okay.
The AI isn't just looking at the ball it's hitting right now, which would be your current math problem. It's actually calculating where the cue ball will bounce 3 steps ahead. It simulates forward trajectories. It calculates, if I give you this medium difficulty problem right now, how does that impact your predicted success on a hard problem 10 steps from now?
That is wild.
It is constantly optimizing for long-term mastery, rather than just getting you to produce an immediate correct answer.
But to predict the future with that level of accuracy, to run those billiard simulations, it needs an incredibly rich stream of data. Like a binary right or wrong ping definitely isn't enough to update those particles.
No, not at all.
It needs to actually watch how you struggle. It needs eyes and ears.
And that is exactly where large language models re-enter the picture, but not as the conversational chatbots we are used to.
Oh, really? How are they using them?
They are deployed as behind-the-scenes behavioral translators.
Behavioral translators?
Yeah, their whole job is to extract deep qualitative signals from your interactions and then feed them into that predictive brain we just talked about.
Okay, this mechanism in the paper totally blew my mind. Let's look at that Pennsylvania system teaching Python.
Yes, great example.
Because if you're a student, you might submit your code like 20 times before it actually compiles and works.
Easily.
Right. And an old system just sees 20 raw failures. It's like, nope, 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 boop. But this new LLM acts as a silent judge doing semantic analysis. How does it actually distinguish a failure from real progress?
Well, an old system essentially just compares your final output to an answer key. If it doesn't match perfectly, it assigns a 0.
Right.
But the LLM actually reads the variables you named and the structure you built. So if you changed a loop structure, but you just forgot to add a colon at the end of the line.
The classic Python mistake.
Exactly. The LLM recognizes the intent behind the code. It realizes, oh, this student fundamentally understands the logic, and they're actively experimenting. They just made a grammatical error.
That's incredible.
It filters out the noise. It realizes that raw submission counts can be wildly misleading.
So it's grading your thought process, not just your spelling.
Exactly. And furthermore, it actually analyzes the dialogue quality when you interact with the system. It scores the conversation itself.
Okay, so think about the last time you were stuck on a problem. Maybe it was a crossword puzzle or some complex software setup at work. Did you go to a colleague and ask for a gentle hint to point you in the right direction? Or did you just throw your hands up and say, hey, what's the answer?
Right.
Because the AI is now trained to know the difference.
Yes. The LLM actively distinguishes between productive help-seeking, where you ask for a concept explanation after proving you've put in some effort.
Like, hey, I tried this, but I don't get this one part.
Exactly. It distinguishes that from lazy answer-seeking. And if you engage in higher quality conversations, the system updates its estimate of your knowledge state. It recognizes that you have effective self-regulated learning behaviors.
Oh, that's so smart.
It literally tells the predictive brain, hey, this student is trying, keep challenging them.
Okay, so the system has these LLM eyes and ears translating my behavior, and it has this predictive brain mapping my future trajectory.
Right.
But if it just hands me a perfectly timed worksheet with the answers printed at the bottom, the sequencing doesn't even matter.
No, it ruins it.
Right. So how does the AI physically orchestrate the environment to keep me in that sweet spot of engagement without giving away the game?
The key is total integration. The paper makes it abundantly clear that siloing the AI tutor away from the system that sequences the content is a massive mistake.
They have to be connected.
They have to talk to each other constantly. And we see a brilliant example of this in an Amazon workforce training program that was designed for linear algebra.
Linear algebra for corporate reskilling. I mean, we are talking about highly complex matrix equations here, not exactly light reading.
No, not at all.
What were the employees actually doing?
So picture an employee trying to master a matrix transformation for a new machine learning role.
Okay.
They hit a wall. They're staring at the screen.
Yeah.
Their error rate spikes. And the system actually senses the frustration.
It can tell they're struggling.
Yes. And because the sequence engine and the AI are integrated, the system doesn't just lower the difficulty or give them the answer to make them feel better. Instead, it matches the difficulty perfectly to their current state and perhaps redirects them to a specific supplementary video explaining the exact step they're missing.
Wow.
And Amazon found that when employees were given these perfectly sequenced learning activities, this magical thing happened. They naturally persisted through difficult concepts.
Because it wasn't too hard or too easy.
Exactly. The matched difficulty made them want to engage deeper rather than just clicking away.
But here is the vulnerability, right?
What's that?
If you sequence the difficulty perfectly, but you leave a generic AI chatbot sitting right next to the problem, the AI completely ruins the learning process.
Oh, 100%.
Because the student gets frustrated, they just type solve this, and the generic bot just blurts out the matrix equation, you lose that matched difficulty entirely.
And that is exactly why the prompt engineering of the tutor itself is absolutely critical. It requires Socratic guardrails.
Socratic guardrails.
Yes. The paper cites research from Brown University on math bots. They demonstrated that chatbots programmed to use Socratic questioning, meaning they answer a student's question with another guiding question, produce significantly better learning gains than bots that just handed over worked examples.
The paper actually calls this effort conditional assistance. I love this concept so much.
That's fantastic.
Like, the GPT-4 tutor in the Penn study literally refused to give direct solutions to the students.
You wouldn't do it.
If a student typed, fix my code, the bot would act like the stubborn veteran teacher. It would reply, I cannot do that until you tell me what you have already tried or what specific part of this function is confusing you.
It's brilliant.
It forced the student to articulate their confusion first before offering any help.
It establishes those pedagogical guardrails. But, this brings up a massive logistical hurdle.
Which is?
Well, to maintain this level of highly personalized, effort-conditional tutoring, you need an almost infinite supply of practice problems.
Yeah.
And at every conceivable micro level of difficulty.
Why?
Human teachers simply cannot write enough content to feed a predictive engine that's simulating thousands of different student paths.
Okay, here's where it gets really interesting, because it begs a huge question. Human teachers spend hours writing just one good quiz that tests a specific concept.
Exactly.
If this AI is uniquely pacing hundreds of kids, it needs thousands of distinct questions. Where is it getting all this material without hallucinating or just giving them total nonsense math?
Right, so the paper details this multi-stage RAG pipeline.
Retrieval augmented generation.
Yes, used in a massive trial in Taipei. And they didn't just ask an AI to write questions, they built an entire factory floor. It's a highly structured assembly line.
Okay, how does that work?
First, a retriever AI pulls the exact curriculum standard required. Then, a generator AI writes a candidate word problem.
Okay.
Next, a totally different AI, I think they used Claude for this, acts as a critic.
A critic AI.
Yeah, the critic tries to solve the generated problem, and it flags it if the wording is too confusing or if the math is fundamentally flawed.
So the AI is literally checking the AI's homework before the student ever even sees it.
Precisely. It creates this automated quality control loop.
Yeah.
And only after the problem passes, the critic does a human teaching assistant do a final review.
Wow.
By chaining these models together, they essentially created an infinite scalable engine for personalized practice material. And it doesn't rely on a single hallucination-prone output.
That is amazing. So you have infinite vetted content, you have a predictive sequence engine lining up the shots, and you have a Socratic tutor stubbornly refusing to give easy answers.
That's the trifecta.
But the ultimate question is, does this elaborate architecture actually work in the real world? Because theory is great, but a classroom full of easily distracted teenagers is like the ultimate stress test.
It really is.
Yeah.
And the paper details a rigorous 5-month randomized controlled trial. They tested this exact integrated system with 770 high school students across 10 different schools in Taipei.
That's a huge sample size.
It is. And the results are incredibly compelling. The headline finding is a 0.15 standard deviation increase in final exam scores compared to students using a fixed traditional sequence of problems.
Okay, I want to pause there. Because a 0.15 standard deviation might sound kind of tiny to someone outside academia.
Right. It sounds like a fraction of a percent.
Yeah, but in educational terms, across a 5-month period, that is roughly the equivalent of bumping a student's final grade from a solid C to a B+0.
Yes.
And simply by changing the order of the questions they're asked and how the hints are delivered?
It is a highly significant bump. But the mediation analysis, like the data explaining why that bump occurred, that is the most crucial takeaway here.
Okay, why did it happen?
Well, they didn't achieve higher scores because the AI forced them to do twice as much practice. And they didn't get higher scores because the AI fed them uniquely difficult, genius-level problems.
So what was the secret sauce?
Sustained engagement?
Just keeping them hooked.
Exactly. The AI wasn't just maintaining difficulty. It was explicitly rewarding itself for keeping learners in what educational theorist Lev Vygotsky called the zone of proximal development.
Oh, I've heard of that.
Yeah. Or, using cognitive psychologist Robert Bjork's framework, the system optimized for desirable difficulty.
Desirable difficulty. I like that phrase. The task is hard enough to make you sweat and force your brain to rewire, but achievable enough that you don't throw your laptop out the window in despair.
That's exactly it. The AI optimized for productive struggle as the primary metric, rather than just rushing the student toward mastery progression.
It paced them.
Right. It realized that keeping a student engaged in that friction zone is both the mechanism for learning and a valuable outcome in itself, because an engaged learner simply persists longer.
So what does this all mean for you listening right now? Obviously, getting better test scores is great, but historically, we've seen educational technology roll out, and it only really works for the kids who are already ahead.
Right. The ones with great study habits.
Yeah. Does this just widen the gap?
This raises an essential question about equity, right? Do these advanced systems leave certain students behind?
Right.
The subgroup analysis from the Taipei trial directly addresses this. The adaptive system didn't widen the gap. It actually closed the achievement gap.
Whoa. That is a massive paradigm shift.
It really is. The data shows that beginner students who entered the class with limited prior experience, they saw a massive 0.215 standard deviation gain.
Wow.
Furthermore, students at lower-tier schools, categorized by their entrance exams, they saw a 0.173 standard deviation gain.
That's huge for those schools.
Absolutely. Meanwhile, the fast learners, the ones who already had extensive experience, they didn't see a huge bump in their scores, but they weren't bored either. They were simply allowed to accelerate through the material at their own pace.
Which fundamentally removes the constraint of the one-size-fits-all classroom.
Exactly.
Because fixed sequences inevitably penalize someone. Usually it's the student who needs just like 10 more minutes to process a foundational concept before moving on. Personalized pacing gives the slower learner the exact scaffolding they need without rushing them, and it gives the fast learner the complexity they crave. It democratizes the kind of deeply individualized pacing that used to only be available if you could afford to hire a private human tutor to sit right next to you.
But, to achieve this level of personalization, the system has to scoop up a mountain of behavioral data.
Oh, yeah?
It is tracking typing speeds, it's semantically analyzing every mistake, monitoring chat logs for effort. When you deploy this to minors, data governance cannot be an afterthought.
Which is a very real concern. How did they handle the privacy aspect in Taipei?
The trial succeeded because it was integrated directly with the government's official e-learning infrastructure, the Taipei Kusi Cloud.
Okay.
They used government-authenticated accounts, they ensured strict adherence to Taiwan's Personal Data Protection Act, and they completely de-identified the data before the predictive algorithms or the researchers ever processed it.
Okay, so it was secure.
Very secure. It proves you can build a highly observant AI system safely, but it requires deep institutional partnerships and rigorous access controls.
It's a heavy logistical lift, but the payoff is just a completely new paradigm for how we approach learning.
Absolutely.
Like whether you are listening to this right now and thinking about reskilling for a corporate job, or you're learning to code on the weekends, or you're just diving into a complex new hobby, the core lesson here is pretty profound.
It changes everything.
The goal of using AI is not to find the answers as quickly as possible.
Yeah.
The goal is to find the exact right level of friction. We are watching AI evolve from this superpowered search engine into a personalized Socratic coach that knows exactly how hard to push you.
If we connect this to the bigger picture,
Mhm.
organizations and educational institutions have to fundamentally rethink their metrics of success.
How so?
We have to stop focusing purely on content delivery, meaning just how fast we can get this information in front of a user's eyeballs.
Right.
And we need to start optimizing for engagement and continuous invisible assessment. The technology is finally here to support productive struggle at a massive scale. We just have to be willing to let the system challenge us instead of, taking the easy out.
And that leaves us with a fascinating, slightly provocative thought to end on.
Let's hear it.
Let's say we fully embrace this. Let's say future AI becomes absolutely perfect at calibrating our productive struggle. Every course we take, every skill we learn on a screen is tailored so seamlessly to our exact cognitive state that we never feel too frustrated and we never feel too bored.
Sounds utopian.
It does. But what happens when we step away from the screen?
Right.
What happens when we have to face the messy, unpredictable, totally uncalibrated struggles of the real world where problems don't adapt to our frustration levels?
That's a great point.
If we never have to learn how to navigate without that perfectly calibrated guide, will perfectly tailored learning make us brilliant? Or will it slowly erode our tolerance for real-world ambiguity? Something to chew on next time you ask a chatbot for a quick fix. Thanks for joining us on this deep dive. We'll see you next time.